An applied force of 70 newtons is capable of keeping a 10-kilogram block at rest on a frictionless ramp. What is the maximum angle this ramp can be? All right, so we'll have our ramp. We have to figure out this angle here, but there's a block on it, and it's frictionless, so it should slide down. However, it's not, because there is a 70 Newton applied force that is holding it there. And the most effective way to aim this force would be directly parallel to the ramp, so that'll be 70 newtons. And that's basically counteracting gravity. Everything's got to be balanced out. This is staying at rest. So what I just drew there, that's not a free body diagram. That's just me kind of thinking out loud there. But I will draw a free body diagram now. So I'll draw my block. Gravity is straight down. Gravity should be split up into components. So I'm going to have a perpendicular to the ramp component and a parallel to the ramp component, which I'll label as FGY and FGX. I better make my definition here, my let statements. I'm going to let X be this way, parallel to the ramp, down the ramp. I'm going to let Y be in the same direction as the normal force, which is perpendicular to the ramp. All right, there's gravity. There's going to be a normal force. The normal force is going to balance out the Y component of gravity, because this block is only going to, well, it's going to be at rest, actually. Everything's got to be balanced. But the normal force balances out the Y component of gravity. So there's an X component of gravity there that also needs to be balanced out. And in this case, it's going to be balanced out by a 70 Newton applied force. So there's a free body diagram, and I'll use double tick marks to represent these components being equal to each other. All right, so normal equals the Y component of gravity. I'll just write that down kind of off to the side. Don't exactly need to use that fact in any calculations here, but they balance. More importantly, to solve this problem, we know that the applied force, the magnitude of it, is going to balance out the X component of gravity. They are going to be equal, and that's the equation I'm going to use to eventually solve for the angle of the ramp, I hope. All right, the applied force is 70. I'll fill that in a bit later. I'll just keep it as applied force for now. The X component of gravity is mg sine theta. The components of gravity, we really want to get used to the two formulas. It's mg sine theta for the X component, mg cosine theta for the Y component. But this is how I'm going to solve for the angle, because I know the mass, I know the value of g, I know the applied force. So I've got everything here that I need to solve for sine of theta. So I'll divide both sides by mg first. And then, so theta is going to be the inverse sine of that fraction there. I'll just fill in the numbers now. So it'll be 70 newtons. In the denominator, it's 10 kilograms times 9.8 for g. So I'll do the inverse sine of that. Get my calculator out here. And I'm getting 46 degrees. Okay, so the The ramp can be 46 degrees, and the 70 newtons will be enough to keep it at rest. If the ramp is steeper than that, then the x component of gravity is going to be bigger than 70 newtons, and it will not be able to keep it at rest. What if the ramp is less than 46 degrees? Well, then we don't even need 70 newtons to keep it at rest. We can use less than 70 newtons to keep it at rest. But if we're capable of applying 70 newtons, then the maximum angle we can support would be 46 degrees.